Okay, today I'm going to review the new antenna that I designed here at my Florida QTH. Last year I used an 80-meter off-center fed dipole fed with ladder line. It worked okay, but it had a serious null into Europe and the Far East on 40 meters. So I needed to design a new antenna this year, and I laid out several important parameters. First of all, it must be a multiband antenna. Second, it should have maximum efficiency on 40 meters, which is my band of choice. Third, it must have peak power focused into Europe, the Middle East, and the Far East on 40 meters. Fourth, it must exhibit positive gain over an isotropic antenna at an elevation angle of 10 degrees. Now, why 10 degrees? Well, to work DX, you must minimize the number of hops it takes for your signal to reach the other guy. So, the lower the takeoff angle, the fewer the hops. Now, the antenna that I decided to use as a starting point was a 40-meter extended double Zepp. Now, the term 40-meter extended double Zepp may not be familiar to some of you, but I'll bet that almost all of you have heard of, and maybe some of you even use, a G5RV. The G5RV started out as a 20-meter extended double Zepp. Some of you may not realize that the G5RV, as designed by Mr. Varney, was designed to be a single-band 20-meter antenna. The window line length was designed to be a proper match to the coax that will be running into your radio room. Now, since then, many people have been modifying this antenna to enable it to work on multiple bands in addition to 20 meters. Now, on my property here, there are several tall pine trees, so height is not a problem. Unfortunately, the trees are not situated properly to provide the directional characteristics I needed using a conventional extended double Zepp design. Also, the beam width of the extended double Zepp was not wide enough to give me the directional properties I needed. So my challenge was to come up with a design that would come closest to the pattern that I needed. Now, each side of the extended double Zepp antenna is 64/100ths of a wavelength long. For my antenna, I chose a length of 170 feet, 85 feet each side of center. Now, further discussions of the antenna and its radiation pattern will be much clearer if it's done on the computer. So let's go inside for a while. What you are looking at is an azimuth projection centered on my location in Florida. This great map is offered to us free of charge by Tom, NS6T. I'll put a link to it in the description. It is a great tool, and Tom deserves a lot of credit for taking the time and effort to develop it. I knew the areas of the globe I wanted to reach, and I also had a pretty good idea of the bandwidth I could expect from an antenna of this type. So I arbitrarily chose 20 to 55 degrees in the northeast direction, which would cover all of Europe, the Mideast, and into India, and 315 to 345 degrees in the northwest direction, which would cover Japan, Korea, Indonesia, and parts of China. If you recall, one of my parameters for an antenna was that it had to have a gain greater than an isotropic antenna at an elevation of 10 degrees. Now, we're looking at the conventional double extended Zepp. So we can see at 10 degrees, we've got almost 3 decibels gain over an isotropic antenna. And that's pretty good. On the left-hand side of the screen, this is our 40-meter double extended Zepp. Now, it's oriented 10 degrees east of north because that's the way my trees are. Now, the red lines that you see here shows that we have roughly 40 degrees of bandwidth. I tried to approximate it. It might be a little bit less, but for purposes of discussion, that would be good enough. So from 260 to 300 degrees to the west, and from 80 to 120 degrees to the east. Now, to put this in terms of a polar projection, our western lobe, you can see, gives us a strong signal into Australia, and New Zealand, but that's really about it. Now, looking at the eastern side, okay, this side here, you can see basically we're going into the southern and then the western part of Africa, the island of Madagascar. Not really a lot of signals down there. Some perhaps rare DX, but not really a lot of bang for your buck in that orientation. So let's see how the 40 meter extended double Zepp did with our parameters. Well, it is a multi-band antenna. We can use it on all bands. It was optimized for 40 meters, and we saw it had good gain over an isotropic antenna at 10 degrees, but it was not so good with our fourth requirement. And that's primarily due to the placement of my trees. The 40 meter extended double Zepp is a broadside radiator, and the way my trees are positioned, it just didn't favor that type of an antenna. So this was my dilemma. Here's my double extended Zepp. It's 170 feet long, and it's oriented 10 degrees north-northeast. And this is the radiation pattern that we just looked at. Now, based on my parameters, this is the pattern right here that I was looking for. So somehow I had to change this into this. Now, in this diagram, all I did was change the feed point from the center, as you can see here indicated by the 1, to 20% off center. So let's see what that did to my radiation pattern. By changing our feed point from 50% center fed to 20% off center fed, you can see how our pattern has changed significantly. Now, comparing it to my original parameters, you can see that we're starting to get into the ballpark here. Now, as far as parameter number 4 goes, we have a positive gain of 0.3 decibels over an isotropic. Now, this is down from the original 40 meter extended double Zepp by a little more than 2 decibels, which is not good, but at least we're getting our RF into the directions that I was looking for. Okay, so now by changing my feed to 20% off center, we came up with this pattern, which was an improvement over the original pattern. However, there were a couple of things that I was not satisfied with. One of which was the big null we have here in this section here, and the other one was the fact that our gain had dropped to 0.32 decibels. Now, what you see on the left is a picture I took of an EZNEC display. Now, you can do many things with EZNEC. One of the things you can do is you can analyze the characteristics of an antenna in both the vertical and the horizontal plane. Now, and it's sort of light, but I think you can see here, what you see in the blue is the horizontal component of the antenna. And what you see in the red is the vertical component. And certainly the horizontal component is substantially bigger than the vertical component. Now, when I saw the placement of the vertical component, I said, you know, if I could increase that, it might fill in this gap here. So what I did was I added a 33-foot quarter-wave vertical section to the end of the double extended Zepp. So, looking at my fourth parameter, I wanted to have a strong lobes from 310 to 345 degrees and from 20 degrees to 55 degrees. Now, looking at what we ended up with, we have a beam width of 115 degrees, all the way from 310 degrees to 65 degrees. So that actually, the 65 degrees actually gives me coverage of most of the northern half of Africa, in addition to everything I wanted in here, plus all of China and India. In addition, we increased our forward gain. If you recall, we were at about 0.3 dB. We're at 2.64 dB, well over 2 dB gain over the previous configuration. So now I've done all my planning. The only thing that remains to be done is go out and build it. So let's go ahead and do that right now. The 600 ohm homebrewed feed line will be attached via the center insulator. After I get the antenna connected at both ends, I'll have this drop to the ground and then I'll attach the feed line. The reason I'm doing it this way is it'll be a lot easier to handle without having all the feed line hanging from it as I try to bring the thing up. Now, this is the short end of my modified 40-meter double extended Zepp. This end is 51 feet, and this part here that you see going out the door, this is 151 feet. I'm sorry, 119 feet. Now what you're seeing here is the far end of the antenna, and the black wire is a 30-foot vertical element that will hang from the end, that will be suspended from the end of the antenna. The antenna as it's designed is basically a horizontally polarized antenna. This vertical element adds a good deal of vertical radiation, which improves my low angle radiation for this antenna. Now there's a shot of the homemade 600 ohm open wire line going up to the center, and I'll pan over. That's the short end of the antenna. Maybe you can see it through the trees there. And as we move off in this direction, that is the longer end of the antenna. Now here's a better view of the ladder line. From here to here is about 18 inches. I space my spacers about every 18 inches. Now there's a shot of the 4-to-1 Ballon and the RF choke, and the black box underneath is the remote antenna tuner, and the length of coax running off to the right is my about 105 feet of LMR 400. Now earlier I mentioned that the components that went into my feed line, I just thought I'd show you what they are. These are just regular, what they call them, stick pins. You can pick them up at Office Depot for Office Max, Office Depot for, I don't know, probably $4 for this. I think was a pack of 48, and then you just take a pair of pliers and just pull this section right out, which pulls the ink and that right out. Then I have a little jig made up where I can just put it in on my saw and cut it in half. And then each section is a little over 2.5 inches. Now I calculated it out, and it's not exactly 600 ohms. It's more like maybe 570 ohms, but that's close enough. And then this is regular speaker wire. I believe this is 18 gauge speaker wire that I use, and 8 inch black cable ties. If you can get the UV resistant ones, you'd be better off. These don't happen to be, these are not the ones I was using. I just happen to have these in the shack, but they're basically the same as I would normally use. Obviously the pens are not UV resistant, but I've had antennas up for, I'm down here in Florida where the sun gets really hot. I've had them up for 4 years, brought it down, and some of them were a little crispy, but basically I really haven't had any problems. So I would say 4 years to 5 years, and you just keep an eye on it, and if you see you're having a problem, you can drop your antenna and just replace 1 or 2 or 3 or however many of them are starting to deteriorate on you. But I really haven't had a great deal of trouble with it, and it's a real simple setup. You can make them very quick. As I said, I space them 18 inches, so 48 of these will give me enough spaces to make just about 100 feet of feed line. And of course your speaker wire is not all that expensive either. So that's just a little bit of an insight into how I make my open wire line. Now by the way, I was wrong when I said you can make about 100 feet of open wire line. With this, with the 48 pins, you can make close to 100, I think it's like 144 or 145 feet of open wire line, which is probably going to be more than enough for most hams. Well, we're here today in my outdoor studio, getting some fresh air. Such a nice day, I thought I'd do this out here. So what I have is a typical wire antenna, center fed. Now this differs from my system in that my system is fed at this point, which is 30% off center. Okay, and that could be a subject for another video. What I wanted to talk about was the amount of power lost, or that could be lost, in your feed line system, irrespective of the antenna, just in your feed line system. So what I did was I took my situation where I use LMR 400, and then I also did a workup on RG8X, because I know a lot of guys out there use RG8X. So in my system, I have 125 feet of 600 ohm ladder line. I should say ladder line. This could be window line too. Now, most guys use ladder line or window line interchangeably. Technically, ladder line is open wire line, and your window line, you know, the plastic, that is called window line. So we have 125 feet of that, and the loss in 125 feet is really not all that bad. It's 0.275 decibels. Now, we take my 105 feet of LMR 400, and we have a loss of over 3 decibels, minus 3.2 dB, which gives us a total system loss of over 3.5 decibels. Now, to try to equate that to power loss, which I think would make more sense, with 100 watts of input on 80 meters, in our 600 ohm line, we're going to lose 6 watts of power. In our coax line, our LMR 400, we're going to lose 53 watts of power. So we have a total system loss of 59 watts. Now, looking at RG8X, our 125 foot of open wire line, that's going to still stay at 0.275 decibels. Now we take our 105 feet of RG8X, will amount to an excess of 5.7 decibels, which gives us a total system loss of 5.9 dB, almost 6 decibels, almost twice as much, not quite, but almost twice as much as with the LMR 400. Now, how does that work out in terms of power loss? Well, again, there's our 6 watts loss in our 600 ohm line. Here's the RG8X. We'll lose 75 watts of power in that 105 feet of RG8X coax, which gives us a total transmission system line loss of 81 watts, which means only 19 watts are going to reach your antenna. So for the heck of it, I said, okay, if I really wanted to have 100 watts reach the antenna, how much power would I have to really put out? Well, with LMR 400, I would have to have 226 watts of output to have 100 watts reach the antenna. With my RG8X coax, I would need almost 400 watts of power to have 100 watts reach the antenna. So this shows just how important your transmission line system is to the overall efficiency of your antenna system. Now, if you're using a system like this with a balance line to a balance and then coax, okay, and then you're using either the tuner in your radio or an external tuner that you have in your shack to quote tune your antenna, this is what you have to be aware of, is that you are going to have this kind of potential SWR and power loss on that system coming in. Now, I've listened on the bands and I've heard some new hams say, you know, my antenna seems to be working fine, it loads fine, but you know, I call guys and they don't seem to come back to me, or when they do, the signal report is not all that good and they just can't quite figure it out. This could be one of the reasons. Now, obviously, the biggest factor is here in your coax and the mismatch in your overall system. So it is going to vary from system to system. Ideally, you want to keep this coax running from your balun to your tuner as short as possible. The losses are also going to vary based on the frequency. The higher you go in frequency, the more loss you're going to have in that coaxial cable. Now, when I was describing my antenna, I misspoke. The antenna is fed 30% from the end, but it's 20% off-center fed. I had those numbers reversed. So the antenna is fed 20% off-center. Okay, now, the setup you see here is if you had no remote tuner. Now, here's the way I have my antenna system set up. Feed line comes down to a 4-to-1 balun, then into an RF choke, and finally into my remote tuner. Now, the remote tuner then tunes my SWR on my coax to 1-to-1. So in terms of power loss, I still have my 0.275 decibels in the open wire line. Now my coax loss is reduced from over 3 decibels to 0.236 dB, gives me a total line loss of a little over half a decibel. Converting that to watts, of my 100 watts, 89 watts are going to hit my antenna, 11 watts are going to be consumed within the system. My RG8X model, 600 ohm open wire line, loss stays the same, 0.275. My coax loss, which was well over 5 decibels, has now been reduced to 0.59 dB, gives me a total system loss of less than 1 dB, 0.86 decibels. Gives me a power loss of 18 watts. 82 watts are going to reach the antenna. That just should give you a good idea as to why you want to be very concerned about your coax. Now, the loss is actually proportional to the feed line, okay? In other words, up here where I have 105 feet of coax and I've lost 3.2 decibels, if I have 50 feet of coax, the loss here will be reduced by a half. It'll be reduced to 1.6. So the key here is, if you're not using a remote tuner, keep the length of coax from your balun to your tuner as short as possible, because this is a situation you're going to be in. You're going to be subject to perhaps large losses in your coaxial cable. However, if you are using a remote tuner, the length of coax is not that significant within reason. I mean, here we have 100 feet of coax. We have a half a dB loss here and 0.8 dB loss there. So that's not a big factor. Well, that's it for this video. I hope you've enjoyed it and also found it informative. If so, please give it a thumbs up. If you have some questions or would like to know more about something antenna related, drop a line in the comments section. I always check that out. If there's enough interest in a particular area, I'd certainly consider making a video about it. If you haven't already subscribed to my channel, click on the subscribe button. If you click on the bell next to it, you'll be notified when I've added new videos. See you next time.